Welcome to our lecture on acids and bases. We're going to talk about the properties and definitions of acids and bases, what makes an acid and base, and what kind of chemical properties they have. All right, we're going to start with acids, and acids have these following properties. Acids taste sour, dissolve many metals, and turn blue litmus paper and many other indicators to the red side of the spectrum of our rainbow. Okay, so acids turn things red. So sour taste, if you've ever had Sour Patch Kids, sour worms, sour whatever kind of candy, that white stuff on the outside might look like sugar, but is not all sugar. In fact, a lot of it or most of it is some kind of acid, malic acid or other kind of acid that tastes sour. And if you've ever noticed, as soon as you suck off all that outside, sugary acid stuff, right, what you get left is a just regular tasting gummy. Also, acids can dissolve metals, and we've actually seen this in the lab where we took magnesium strips of metal and we put them in hydrochloric acid, and we saw little bubbles coming up from it, and saw the metal slowly start to disappear as it dissolves. And then finally, acids, like I said, turn indicators like blue litmus paper or universal indicator, cabbage juice, any of those kind of indicators that rely on color. Acids will turn them to the red part of the spectrum. Okay. So some examples of some acids. Hydrochloric acid is a very common one. So common it's found naturally inside of you. Hydrochloric acid is the kind of acid that is in your stomach, starting to break down proteins and kill bacteria and other harmful bugs that you might swallow with your food. But hydrochloric acid is also used in industry, for example, to clean off and make metals shiny, to prepare and process foods, and to refine metal ores. So hydrochloric acid is a big, very, very common acid in our world, along with sulfuric acid and nitric acid. And these guys are used in labs, fertilizers, explosives, car batteries. Your car battery is sulfuric acid based, and whatnot. So we've got acids, in common places around our world. All right, here's one other example of acids. We have acetic acid, which is an acid that we use oftentimes in cooking and preparing foods. Vinegar is a common name for acetic acid. So anytime you're using vinegar in a recipe, or if you look at the ingredients, like for example ketchup and mustard, use vinegar to make those products. Just know that vinegar is a common name for acetic acid. Vinegar is, or acetic acid, I should say, is also produced when wine is stored improperly. So if it has like this sour taste when you open it, when you're much older, obviously, and can actually drink. But if you'll know a bad wine if it tastes and smells sour. Now, the reason why the acids taste sour is due to this carboxylic acid group. Okay, so it actually has the name in its, the acid in its name. Carboxylic acid is basically it's what we call a functional group. It's a group of atoms in a molecule that give us certain behaviors and react in certain ways. And so this C with the double bond O, and the C is also bonded to an OH group. We call that a carboxylic acid. You'll find out more about those in chapter 18. But in any case, it's found in lots of different living organisms, and it makes up the reason why the acids taste sour. Okay. All right, so shifting over to bases, just kind of looking at their properties. Bases taste bitter. So sour is one taste and bitter is another taste, and both for me are definitely not pleasant tastes, because honestly they're protective. We're created with this ability to be able to detect plant poisons, which a lot of basic substances called alkaloids are what we call plant poisons. So back in the earlier days when we didn't have as much information about the plants growing around us and haven't studied, what they do and the properties and whether they're good to eat or not. A lot of it was human experimentation with just taking a bite. And, the ones that tasted really bitter and gross, they found out kind of killed people. So bitter taste is common in bases, and bases make most of the plant poisons. All right, bases also have a slippery feel. So if you think about, with soap, bar soap, or even, the hand soap, this feels all slippery. That's a property of bases because bases are used to make soap. And in terms of litmus paper and other indicators, bases are going to turn to the blue side of the spectrum of our rainbow. So acids turn red and bases turn blue. Little alliteration there, bases blue, to help you kind of remember which color. So some examples of bases, we've got sodium hydroxide, all right, which is actually used in soap making and plastic manufacturing, and maybe most commonly you've had to use it to unclog pipes in your house because it's the main ingredient in Drano. Potassium hydroxide could also be used as Drano as well in making soap, and is also used in cotton processing. All right, sodium bicarbonate is another acid that's a weaker acid, but so it's a weaker acid, so it can be used as what we call an antacid to help neutralize stomach acid. So we choose little tablets of Tums or Mylanta or any of those other kind of acid, quick and easy, like chew and swallow acid reducers probably have sodium bicarbonate in it to help neutralize the stomach acid. Sodium bicarbonate is actually the chemical found in baking soda, which is used often in cooking, and is a great source of CO2 when it reacts with other things. All right, so let's get into the kind of definitions of acids and bases. So we talked about their properties and where they're found. Now let's get into the chemistry of acids and bases. So there's actually, we're going to find out 2 definitions of acids and bases. An earlier one and then an expanded definition, because we're going to find out that this first definition doesn't quite cut it for some substances in terms of acidity and basicity. All right, so the first definition is called the Arrhenius definition. Back in the late 1800s, a Swedish chemist named Svante Arrhenius basically came up with this first definition. Acids produce hydrogen ions in solution. So in his experiments, he noticed that acids produce hydrogen ions and bases produce hydroxide ions, which is the OH minus. So acids have an H plus ion that gets kind of broken apart and into solution, and bases produce OH ions in solution. So hydrochloric acid is an Arrhenius base because when we put it in water, it breaks apart into H plus and Cl minus, and that presence of the H plus there means that it is an acid. Now, in reality, that H plus is actually, let's go down here to the bottom, that H plus is actually going to be reacting with water itself. Okay, so this H plus given off by the acid actually reacts with H2O to make this what we call hydronium ion, H3O plus. And that's what we're actually going to see chemically. Although for shorthand, we kind of just say the H plus or the hydrogen ion. More of that in solution means that is an acidic solution. Okay, but realistically, what we're going to be seeing is this H3O hydronium ion. All right, so when we see the molecular formula for an acid, we're always going to see an H out front. And this H out front is what we call the ionizable hydrogen. That's the one that comes off. All right, so that dissociates, right, and reacts with water to make that hydronium ion. So it comes off, and reacts with water. So we might see other H's behind it, like this H here, but this is non-ionizable, meaning that it stays intact, okay, to the rest of the molecule. So here we're going to have one H come off to give us our H plus floating around to make it acidic in nature, and then this one here, this other H, stays intact. So real easy way to figure out if something is an acid or not is to see if the formula starts with an H. If it does, it is likely an acid. Shifting gears over to bases, the first definition of an Arrhenius base is one that produces hydroxide ions in solution. Okay, so hydroxide ions is the OH with the little minus. It's a polyatomic ion with a negative charge. So this example here, NaOH, in water is going to ionize or dissociate, we call it. It's going to dissociate, which just means to break apart, into sodium ions and the hydroxide ion. And the presence of this hydroxide ion in solution makes a solution what we call basic. Okay. Now, if you recalled, a acid gives off H plus ions, right? A base gives off OH ions, and if you add those two together, H plus OH, you get H2O, which is neutral. So that's why we can, quote unquote, neutralize an acid with a base or neutralize a base with an acid, because if we get the right amount of H's and OH's in the solution, they will all find each other to make water. Okay, with nothing left over, no acid or base left over, then it's what we call neutral. So there are a few limitations on this first definition of acids, this Arrhenius definition of acids and bases, like I mentioned before, which is going to lead to our second definition, or an expanded definition of acids and bases. And the main limitation of the Arrhenius definition is that it cannot explain why some substances that act like bases, meaning that they give off hydroxide ions in solution, don't contain OH themselves. All right, so up here we saw NaOH, right? There's our OH that's going to break apart and go into solution there. But some bases don't have the OH in the formula. So how are they going to be able to, give off or increase the hydroxide ion concentration in a solution? So that's where our second definition is going to explain. All right, so about 40 years later, 1923-ish, we've got the Bronsted-Lowry definition of acids and bases. And so with further work and finding out that limitation of, base definition according to Arrhenius, Bronsted-Lowry is going to focus on the transfer of hydrogen ions in a base and acid reaction. Okay, so we're going to have an acid that now is going to be not just something that increases the hydrogen ion concentration in a solution, but is actually a proton or hydrogen ion donor. Okay, so an acid is going to give the hydrogen ion, okay, to another chemical in the substance. Okay, and we call that a proton donor, because if you think about it, hydrogen is atomic number 1, so that means it's got one proton, right, and one electron. And if he loses that electron, what's left? Just the proton. Okay, so anytime you see hydrogen ions, just know that those are literally protons in solution. Okay, so bases, on the other hand, are going to be proton acceptors. So they're going to get or gather be attracted to those hydrogen ions. Okay, so the hydrogen ion acceptor is a base, and the hydrogen ion donor is what we call an acid. So looking at HCl, okay, with this Bronsted-Lowry definition, it becomes clear that the hydrochloric acid, HCl, okay, in this equation here, if we look at the before and after picture, we can see that HCl loses his H, right? Because he starts with HCl and he ends with just Cl minus. So he loses his H, so that must have meant that he is a proton donor. And so what that means is that HCl gives the H to H2O, so that H2O is now H3O. You guys see that? So proton donor is going to give its hydrogen to something else in solution. In this case, it's water. And now water becomes H3O, and HCl is now just left with this chlorine ion. Okay, so it works. That definition, both definitions work just fine for hydrochloric acid. All right. So let's see some more examples. So in terms of Bronsted-Lowry bases, okay, remember bases are going to accept the proton from the water. So if we mix a base like NH3 here with water, if we look, we always have to look at the before and after picture of what was going on with the hydrogen ion. Who gives it and who takes it? That's going to be basically the two questions that you need to answer as you're looking through these examples. So in this case, we start out with NH3, and on the other side we end up with NH4. So that means the hydrogen ion must have been taken or accepted by NH3, right? So one of these H's goes to NH3 in order to make NH4 in the end. And if a water molecule gives up one of his hydrogens, what does he have left? OH minus. All right. And what was the definition of the Arrhenius base? One that increases the concentration of OH minus hydroxide ions, right? So even though that NH3 does not have OH specifically in its formula, like KOH or NaOH, right? He is still a base because he is increasing that hydroxide ion concentration by taking, okay, the hydrogen away from water. Does that make sense? So that's what they were getting puzzled about in the early 1900s was, hey, this substance doesn't have OH in it, doesn't have a hydroxide ion in it itself. How is it still increasing the concentration of hydroxide ions in the end, in the solution? And so this is what they figured out. The NH3 must be taking a hydrogen away from water to leave behind the hydroxide ion in solution. All right, so taking a look at a couple more examples, we can always see that acids and bases always occur together, right? Always. One of these, if it's giving away its hydrogen ion, the other one needs to accept it. Okay, so we have an acid and a base, right? Or if one's taking it, then the other substance has to be giving a hydrogen ion as well. So, like I said before, you always have to look at the before and after picture and see what's going on. So here, HCl, right, is giving away a hydrogen ion to water, so water becomes H3O instead of H2O, and then HCl just ends up as Cl minus. Okay, so because HCl gave away its proton, that makes it a proton donor or acid, right? And because water was the one that took the hydrogen ion or the proton, he is the proton acceptor, and that makes him a base. All right. In the second example that we saw, the NH3 was the one that was taking the hydrogen ion from water to become NH4 now, right, with a little plus sign. And that means water was left naked as hydroxide ion, OH minus. Again, still going along with the Arrhenius definition of increasing the hydroxide ion concentration in solution, but not because NH3 has OH or hydroxide ions in its formula, but because he is taking the hydrogen away from water. Okay, so in this case, he accepts a proton, making it a base, and water is giving the proton, making it an acid. So we're going to see that water can act as both an acid and a base. Okay, so we'll get to that that special property of water acting as both an acid and a base in a few minutes. Let's take a look at what we call a conjugate acid-base pair. Okay, so most of these kinds of reactions you guys are going to see have a double arrow. Okay, a double arrow between the products and the reactants, and that is indicating the fact that it is a reversible reaction. So that means it can go in either the forward direction or the backwards direction. It's reversible. So we can have NH3 plus H2O reacting to make NH4 plus OH, or okay, in the backwards direction, NH4 and hydroxide ion can react with each other to make the NH3 and the H2O again, right? So that's what a reversible reaction is. So we have to be careful in what we call an acid versus a base, because if we're looking in one direction, a certain substance is going to be an acid, but in the opposite direction, it's going to act like a base. Okay, so in order to make that distinction between the forward reaction and the reverse reaction, we add the prefix, or not prefix, but the word before acid and base. We add a conjugate. Okay, like opposites, or it kind of, actually they're paired. Okay, so let's see how that works. So NH3 in the forward reaction is taking a hydrogen away from water, right? If he's taking a hydrogen, that means he's a base. So in the forward reaction, NH3 is the base and water is the acid, since he's donating that H. And so we would just, in the forward reaction, call them acids and bases. But if we take a look at the reverse reaction, in the reverse reaction, we start out with NH4, and now he's going down to NH3. So that means he's giving away a hydrogen ion back to the hydroxide group, right? So that means this guy is our acid now, okay? So the nitrogen molecule on the left side was a base, but looking in the opposite side, it is an acid, because now he's giving away its hydrogen ion back to OH. And so if OH is accepting this hydrogen ion in order to make water in the end, then that makes him a base, because remember, bases are proton or hydrogen ion acceptors. Okay, so like I said, the same the same root species, the NH molecule on both sides, is acting as a base in the forward reaction and an acid in the reverse reaction. So we need a way in order to distinguish the two, right? So in the forward reaction, we just use the regular terms acid and base, and the backwards reaction, we use the word conjugate before. So we say conjugate acid and conjugate base. Okay, so in this forward and reverse reactions, a base accepts a proton, becomes a conjugate acid, and an acid accepts or donates a proton and becomes a conjugate base in that reverse reaction, right? So these guys are happening in reverse. All right, so let's take a look at a couple of examples here and identify which one is the acid, base, conjugate acid, and conjugate base. So looking here in the first one, in the forward direction, we have H2SO4 and water makes H3O and HSO4. So we have to look at each species separately in that forward reaction. So let's start with the forward reaction. First, we're starting with H2SO4, and in the end, we just end up with one H. So that means this H2SO4 is actually giving away one of his hydrogen ions to water, okay? So if you give away, right, then that means it is an acid, okay? Give away means a donor, right? It's donating a proton or a hydrogen ion, so it makes him an acid. Now, water in this case is going from H2 to H3, so that means he got or accepted or took that hydrogen ion, so that makes him a base. I can spell it right, base. That makes sense? Okay, so in the forward reaction, H2SO4 gives away one of its H's to water, So that means H2SO4 is the acid and water becomes the base since he accepted that hydrogen ion. Now, this also applies to the Arrhenius definition. Here we've got the H out front, so we know it's an acid, right? So it's another way we can identify. All right. Now in the reverse reaction, though, we're going to see the opposite happen. So in our reverse reaction, H3O now goes down to H2O. So that means in this one, H3O is giving, and so he's the acid. But remember, on that side, we call it conjugate acid, right? And H2SO4 is the one that's receiving because he starts out with 1 on this side and 2 on the other side. So that makes him, if they're receiving or getting an extra proton or hydrogen ion, that makes him a base. So conjugate base. So just have to remember who gives, who takes, and in the reverse reaction, just put that conjugate word beforehand. Okay. All right, let's take a look at the next example. We have got, again, we have to look at the before and after reaction, the reactants and the products. So in the forward reaction, we're going to start with looking at that one. We have 1H, so H1, right? CO3 becomes H2CO3. Okay, so in order to become H2CO3, it had to take a hydrogen ion. So takers are bases. So HCO3 is a base. Okay, so that means it must have took in a hydrogen from water. So let's see if that happens. So water starts with 2 hydrogens and now only ends with 1. So that definitely is the case where water gave a hydrogen to HCO3, and so if you give away your hydrogen, you are an acid. Okay. Now, this is a reversible reaction, so looking at the reverse, okay, starting with the stuff on the right and going to the left, we can see that we start out with 2 H's and H2CO3, and we end up with just 1 on the other side. So that means he gave away or donated one of his H's in this case, and so we call that an acid. But remember, if we're looking in the opposite direction, it's going to be what we call a conjugate acid. Okay. And this H has to go somewhere. In fact, that H went to the hydroxide ion here to make H2O in the end, to make water. So if he accepted, that means he's a base, and if we're looking in the reverse direction, we call that a conjugate base. Okay, so like we saw before, the base substance is always going to be a conjugate acid on the other side, and an acid is always going to become the conjugate base on the opposite side. Okay, so again here, the acid becomes the conjugate base, and the base becomes the conjugate acid. All right, so here's a couple for you to try. So again, just like last time, you're going to identify the acid, the base, the conjugate acid, and the conjugate base. Okay, and then so go ahead and pause it and try it on your own, and then you can unpause it to see if you did it right. All right, so hopefully you guys got these right. So in the first one, C5H5N is the base, since he's taking a hydrogen, right, on that side. He's got an extra hydrogen, so that makes him the base in the forward reaction. And so water must have been the acid giving away its hydrogen. And in the opposite direction, that extra hydrogen on the C5H5N molecule goes away. And so that means that that molecule must be the acid, since he's giving up that hydrogen. And OH minus must be the base, since he's accepting or taking that hydrogen ion. And then the same thing on the bottom, HNO3 is the acid, making water the base. And in the opposite direction, we have NO3 is the conjugate base, and water must be the conjugate acid. All right, so if we are talking about acids and bases, then we must be talking about neutralization reactions. And we've actually seen neutralization reactions before in the reaction types chapter. I think chapter 7, I believe. So in last unit, it was, we talked about neutralization reactions, and here we're going to take a look a little deeper about how or why that works. So when you mix an acid and a base together, that hydrogen ion from the acid is going to combine with the hydroxide ion from the base to form H plus OH always makes H2O. Okay, so anytime you've got a acid in front hooking up with a base, okay, then you're going to make water, and then the other two things that are not making water, in this case K and Cl, are going to make what we call a dissolved salt. So dissolved meaning that it will be able to dissolve in water. You won't actually see it come out of solution. It'll be dissolved in, mixed in. Okay. So in general, right, we've got an acid-base reaction making water and a salt. A salt is any ionic solution, or any ionic compound is technically in chemistry called a salt. In everyday life, salt means NaCl, the sodium chloride version of salt. But to a regular chemist, any ionic substance is considered a salt. Okay. So if we were to take a look at the net ionic equation, and we did these back in Unit 2, with breaking apart all of the aqueous substances into their ions and figuring out exactly which ions are taking part in the reaction. That was our net ionic equation. So for neutralization reactions, every single time that you have a neutralization reaction, you are always going to be taking hydrogen ions and hydroxide ions and making water. And water is a liquid. That should be a lowercase l. All right. So that sticks together. All right. So it's not going to be aqueous. It's going to be liquid water, which is going to stick. So our net ionic equation for neutralization reactions is always H plus OH minus reacts to form water. All right, we had mentioned in the first slide on acids that acids can dissolve many metals. Okay, so a reaction between an acid and a metal is usually always going to produce what we see hydrogen gas. Okay, so hydrogen gas gets produced, so those bubbles, in fact, we did this exact experiment in class. Those bubbles that we see coming off of the magnesium is hydrogen gas. All right, and if you remember, either in this year or in regular chemistry, we put a cap on it, all right, and then kind of built up that hydrogen gas solution, the hydrogen gas in the test tube. We took it off, lit a match, and you heard a pop, right? Because hydrogen gas is very flammable. Okay, so it reacts with oxygen. All right, so every single time we have an acid eating away a metal, we're going to have hydrogen gas being formed. And then, so here, if we take a look here at this first one, if hydrogen is going to make the metal, then what we have left over is what is left over in that aqueous solution. So in this case, it's magnesium chloride. Okay, making sure you crisscross the charges, right? Mg plus 2, Cl minus 1. Crisscross the charges to get the correct formula. Okay, so always making hydrogen gas and then some kind of dissolved salt in the end. So same thing here with the second one. We have H2SO4. Okay, the H out front is going to be making the hydrogen gas, so that means Zn and SO4 are going to hook up to make our dissolved salt, our aqueous zinc sulfate. Okay, so I mentioned before that some metals are going to be able to be dissolved by acids, but not all metals. And we talked about the activity series in Unit 2 as well. We'll speak about it again when we get to Unit 16. But the ones lower on the activity series, the bottom of the list, are going to be the ones that are not be able to dissolve in water. So those are the precious metals like gold, silver, and copper. Those guys do not get dissolved by acids, okay? Which is a good thing because, if you think about it, gold and silver are what we use to make jewelry, rings, and everything like that. So if those, if we're cooking and an acid gets on them, we don't want our jewelry to be eaten away, right? And then copper is used a lot in pipes and especially for water pipes. And so we don't just in case we throw a bunch of vinegar down the sink, or somebody's battery's leaking and it gets into the water supply, we don't want that acid being able to eat through the pipes, right, and cause damage there. So copper is one of those other ones that do not get readily eaten or reacted with acids. All right, so acids can also react with metal oxides. Okay, and we've seen these before in Unit 2 as well. So with metal oxides, we're going to get water and a dissolved salt again. Okay, so basically if you just kind of look at this as a double replacement reaction, those words should be familiar to you. So H is going to hook up with O to make H2O, right? And Cl is going to hook up with K to make KCl. And every time you do that with a metal oxide, so for example, the same thing on the bottom, H and OH make water, MgBr make MgBr2, right? Every time you do this, you will always end up with water, H2O, plus any kind of dissolved salt. So this almost looks like a neutralization reaction as well. But in this case, it's not an acid and a base, it's an acid with a metal oxide. Okay, so if we're talking about all these types of reactions, we better be able to write them out. Okay, so we're going to have some example problems in here where we have to write out the reaction between two substances and figure out what they make. So the first one is the reaction of hydroiodic acid with potassium metal. All right, so here hydroiodic means we're doing H with iodine. Okay, so we do need to make sure that we crisscross the charges to make sure that they're neutral substances. So H is a +1, I is a -1, so this is just HI. And then we have potassium metal, that's K. Remember, anytime we're working with an acid and a metal, we're always going to get those bubbles, which are hydrogen gas, so H2. Not just H, because he's a diatomic molecule when he's by himself. So that means he always hooks up with like a twin H. So H2, and then what we have left over, right, is K and I. So we need to hook up K, which is a +1, and I, which is a -1. So we're going to have Ki in the end. Okay, so this is going to be aqueous. And this is going to be gas. Okay. So if it's difficult to remember, what exactly the products are going to be in the end, and if you've got a better kind of grip on single replacement versus double replacement, you can see that, then do that too. Okay, you don't have to memorize, exactly, what acid and a metal make, or acid and a metal oxide make, or acid and a base make. Okay, you can just do the coinciding single or double replacement reaction. So like in this case, we said, okay, well, we've got a compound and we have a single element, so that means K is going to kick out H to become H2, and then K is hooking up with I to become Ki. Okay, so you can go back to those types of reactions too in order to figure out how to write these out. Okay, all right, the second one, the reaction of, let's go back to the first one because we need to balance it. Okay, every time you write a reaction, you want to make sure you balance it. And this is not balanced since we have two H's on the right and only one on the left. So we need to put a 2 in front of HI, which gives us two I's on both sides. So we need to put a 2 in front of KI to balance out those I's. And now we have two K's on the right, but only one K on the left, so we need to add another 2 right there. Okay, so 2, 2, 1, 2 is our coefficients for that first reaction. Okay. All right, let's take a look at the second one. We have hydrobromic acid with sodium oxide. So hydrobromic, remember we talked about in the first unit with nomenclature. Hydro means that it's the kind that starts with H out front. And then bromic means it's just the bromine atom. It's not a polyatomic ion. Okay, so we have to crisscross the charges. H is a +1, bromine is a -1. So in this case, you just need one of each to cancel each other out, right? HBr. And he's going to react with sodium oxide. So sodium and oxygen are hooking up. Sodium's a +1 charge, oxygen's a -2 charge. So this one doesn't cancel out right away, so we do need to crisscross those numbers. So we're going to end up with Na2O1. Okay. So here is our here's our reactants. That's what I'm trying to say. Here's our reactants, HBr and Na2O. And now we have to figure out what they make in the end. Now, if you memorized that anytime you have an acid and a metal oxide, you make water and a dissolved salt in the end, that's great. But like I said, if you haven't memorized that yet, or you don't think it'll stick, just use our rule for double replacement, right? Switch the metals with each other. Okay, switch the non-metals with each other. So H, instead of being with Br, is going to hook up with O, right? Every time that happens, we need two H's to cancel out that O. So we have H2O liquid being formed. And then we're going to have Na, the sodium, the metal atom, hook up with Br, the non-metal atom. And in this case, Na is a +1, Br is a -1, so that's just NaBr, right? And that one is aqueous, dissolved in water. You could look up on the solubility chart just to make sure, right? That one is dissolvable in water. But remember, alkali metals are always dissolvable in water, no matter what they're hooked up with. Okay? All right, and then we have to balance it. So we've got one H on the left, two on the right. So let's put a 2 out front to balance the H's. We've got two BRs now on the left and only one on the right. So we need to balance the BRs out by putting a 2 in front of NaBr. Now we've got two NAs on the left and two NAs on the right, and one O on the left and one O on the right. So just putting a 2 in front of HBr and a 2 in front of NaBr, we balanced it out. All right, so here is where you guys are going to pause and try this on your own. So this is a skill that is basically going all the way back to Unit 1, nomenclature, right? Being able to look at a name and write the formula for it. And then also Unit 2, where we learned about the types of reactions, single replacement, double replacement, to help us figure out what is going to be made in the end, right? Go ahead and pause this, do these two, and then you can unpause it to make sure you did it right. All right, so here are the balanced chemical reactions for both of these examples. So make sure you check yourself, make sure you have the correct products in the end with the correct formulas for them by crisscrossing the charges or realizing that hydrogen is a diatomic gas, so it forms H2 instead of just H. And then also make sure you've balanced it. And in the end, for these ones, it is important to put the states of matter. That's what I'm trying to say. The states of matter there, so that we know what type of substance we're talking about. So if we see G, we know it's a gas, so we can think, okay, it's going to make bubbles, right? And knowing that H2O is a liquid that's sticking together, we know the reaction actually has occurred, and it's not that no reaction occurred at all. All right, so your book kind of writes off base reactions, and that's fine because at the intro level that this is, it's not a huge deal to know about any important base reactions, because most of the important base reactions are those that actually are neutralizing acids. The only other kind of base reaction that your book found important enough to tell you was that sodium hydroxide can react with aluminum. Okay, so most metals are going to be able to be reacted with acids, and to produce something else. But aluminum actually can be reacted with a base to make something else. All right, so we can get a gas from aluminum by reacting it with sodium hydroxide. Okay. So aluminum is one of the few metals that dissolves in a base. All right, so with all this talk of neutralization, right, and acids being able to react with bases to make water, which is neutral, and we'll talk more about that when we talk about the pH scales in the next video. Okay. we come to this idea of titration, and we're actually going to do a lab with titrations. And a titration is a reaction where we have a solution of a known concentration. So we know the solution of one concentration. And we use that in order to figure out these concentration of an unknown solution. Okay, so say we have a solution of unknown HCl. Like somebody mixed it up in the lab and diluted it, whatever, and they forgot to write down what the concentration was, right? You can't just throw it down the sink, right? We've got to make sure it's neutralized first. And so in order, to figure that out, what we need to do is called a titration reaction. And we can figure it out if we know the molarity, right, or the concentration of a base like NaOH. So if we know that molarity, we can use that in order to figure out the molarity of the unknown HCl. Okay. So in the lab, you'll have the same idea or setup. We're going to have the unknown acid. Okay, for you guys, it's going to be vinegar. We're going to be figuring out the concentration of vinegar. So we have the unknown molarity of acid in the flask below, and in the burette tube up here on top, you're going to have the known molarity of the base. And so what you'll be doing is adding drop by drop, okay, base into the acid until it turns pink with this indicator. So let's see how this works. So as we're adding that H2O, right, from the burette tube into the acid, as we're adding it drop by drop, it's reacting and neutralizing the hydrogen ions to form water. Okay, and so a titration is going to be complete when it ends at its what we call the equivalence point, where the hydrogen ion concentration is equal to the hydroxide ion concentration. Right? So we have the same number of moles of hydrogen and moles of hydroxide, so that they're coming together to make nothing but water. And then nothing left is left over. There's no extra hydrogen ions. There's no extra hydroxide ions. It's completely equal. That's what we call the equivalence point. Okay? And this equivalence point is going to be signaled by what we call an indicator. And we have to make sure that we put the indicator in for our reaction. Okay, an indicator is just a dye whose color is going to depend on the pH of the solution, how acidic or basic the solution is. So that's what an indicator is. So in our lab, we're going to use the indicator phenolphthalein, which is clear in acidic solutions and turns super dark pink in basic solutions. So if we can get drop by drop, and get it to be a super light pink, we know that we've basically made, as neutral of a solution as possible. All right, if it's super dark pink, that means you've added too much too fast, and now there's more base than acid. But if you can get it a very, very light pink, all right, we can know that it's pretty much neutral. Okay. So at neutral, that means the moles of the acid are equal to the moles of the base. All right, meaning that we have, equal numbers of hydrogen ions to hydroxide ions to make water molecules, and there's nothing left over. So when we do this, when we reach that equivalence point, we can determine the concentration of the unknown solution. And this is how we use this famous equation, M1 times V1 equals M2 times V2, okay, to figure out the concentration of our unknown acid. And we just saw this equation in chapter 13 when we're talking about molarities and dilutions, right? So we're talking about dilution chemistry, where we have a concentrated acid and we want to dilute it to a less concentrated acid. So we use this equation, right? And we figure out what volume of acid we need in order to, and what volume of water in order to make it a less concentrated acid. So we're actually going to use this again for acid and base titrations, okay? Because at the equivalence point, remember the moles of acid are going to equal the moles of base. So in this equation, if we plug in all of the left side with our acid information and all of the right side with our base information, acid is going to equal base, all right, at the equivalence point. So here's an example question. It says the titration of 10 milliliters of HCl of unknown concentration, right? So we have no idea what the concentration of HCl is. Okay, it requires 12.5 milliliters of a 0.1 molarity NaOH solution. So if we had 0.1 molarity and we added 12.5 milliliters of that, we would get that light pink color where it tells us that we reached the equivalence point. So it's asking, what is this concentration of unknown HCl? So again, if we use M1 times V1 equals M2 times V2, acid equals base, we're going to plug, we're actually going to be solving for M1 here. We need to figure out the concentration of the acid. So dividing both sides by V1, right, like I did here, and we plug all that information in, right? So the molarity of our base is 0.1. The volume of the base that we used is 12.54, right? The milliliters of acid that we had in the beginning was 10 milliliters. Okay, so if we solve that math, right, the milliliters are going to cancel, and we're going to end up with molarity in the end. Okay, so 0.125 molarity was the concentration of our unknown acid. And we found that out by using our dilution equation. M1 times V1 equals M2 times V2. All right, so here's one for you to try, and this is our last slide, so we made it to the end. All right, so this one says the titration of a 20 milliliter sample of H2SO4 solution of an unknown concentration, right? So here's it's an acid because it's got the H out front, right? So we need to figure out what molarity of the acid. Okay, it's going to require 22.87 milliliters of a 0.158 molarity KOH solution to reach the equivalence point. What is the concentration of H2SO4? So go ahead and pause this, do this on your own. Okay, use the equation there, do it on your own, figure out M1, the concentration of the acid here, and then unpause it to see if you did it correct. All right, hopefully you ended up with 0.181 molarity of our H2SO4 solution. All right, so that concludes this first half of the chapter on acids and bases, chapter 14. And if you've got any questions, just let me know.